Hey, what's up guys? My name is Cherno and welcome back to my OpenGL series. So today we're going to be talking all about textures in OpenGL, and we're going to start by defining what exactly a texture is. So when most people think of textures, they really just think of having an image on a 3D object in a game. And it doesn't have to be a 3D object, of course, but some kind of image that you've created in something like Photoshop or Paint or whatever, having that on some kind of surface in your graphical application. That is essentially what a texture is, or at least that's how most people actually kind of think of a texture. Now, beyond that, textures can really be a lot more than just what I just described. Textures can be used really for a lot of things, and we'll discover that when we get into some pretty complicated graphics techniques. But for now, I just want you to think about a texture as essentially an image that we can use when we're rendering something. So what I can actually do is design or create some kind of image, whether that be a photograph or maybe just a squiggly line on a canvas, or maybe like a kind of solid color or something like that, anything like that. I can create any image file on my computer, and then I can actually upload it to my GPU's memory and use that in my shader for whatever kind of drawing I'm doing. Now, this might be something as simple as just drawing a rectangle in our OpenGL program that is actually rendering that texture so that we can see the texture in our game. Or it might be something a lot more complicated, like using kind of pre-calculated mathematical values that are baked into our texture and then being able to sample them in our shader so that we can do some cool lighting effects. But for now, it's just going to be getting an image from our computer onto a surface in our OpenGL application. So let's take a look at what we've got here. So if we launch our application right now, just so that we can remember where we're actually at, you'll see that we just had this kind of rectangle with a pulsating color. Now what we're going to do today is actually draw a texture on that rectangle instead of this kind of solid color. Now if I look at my actual directory for this OpenGL program, I've made this resources folder, and inside there I've made a folder called textures, which just has a single image, and it's going to be this Cherno logo that I have here. This is what we're actually going to draw on top of that rectangle that we have in our program. So how do we do that? How do we go from having a physical kind of PNG file on our computer to actually being able to sample it in our shader so that we can draw it on the screen? How does that work? Well, step one is we need to load that image somehow into our CPU memory, right? So in this case, it's a PNG. Now, I'm not going to get into how games use textures and what formats all that we'll say for the game engine series. PNGs aren't really used in game engines. Most game engines have their own texture format for various reasons. But for now, just because again, this is all about loading OpenGL, we do have a PNG image file. So what we need to do is load that somehow. Now, PNG format isn't particularly complicated, but there are a few kind of, there are a few different pixel formats inside there, as well as primarily the option of having a compressed PNG as well. And there's a bunch of decoding that we actually need to do to get the data out. So what we're going to do is we're going to use a library for that. And specifically, we're going to use something called stb image, which is a very, very small, it's one file. That's all we're going to do. We're going to get it from GitHub in a second here. But all we need really is one file, and we're going to use that to actually load the PNG. Now, when I say load the PNG, what I mean is we give it a file path. So this is my file on my computer. And what it's going to do is give us basically a pointer to a buffer of RGBA pixels, which is what we actually want to then take to the next step, which is going to be taking that pixel array and uploading it to our GPU. And the way that we do that, of course, is through OpenGL, because OpenGL is our graphics specification. So we use OpenGL to then send that data into the GPU as a texture. Once we've done that, we can modify our shader to actually read that texture when it's drawing. So the pixel shader, the fragment shader, is going to read from that texture memory and actually work out which pixel should be which color as per that texture. And that's what will happen when we actually draw that rectangle of ours. So just to recap over all of that, and there are some detailed steps kind of in between that we'll address definitely, but that is the gist of it, right? We load our image, we create a texture in OpenGL, we then have to bind that texture when it's time to render. We modify our shader to also kind of bind to that texture slot that we've bound our texture to, and we also sample that texture in our shader, and when we draw our rectangle, we should see the texture. So let's just go ahead and write some code. So the first thing that we really need to do is load this image somehow into our CPU memory so that we can send it to OpenGL. So over here, what I've got is a GitHub repository, which I'll link in the description below. And inside this kind of STB library, which is single file public domain libraries for C++, so you can use these completely free, there's something called STB image. And really there's just this one file. That's all we need. I'm going to open that file. I'm going to click on raw here, and just to make this really simple for myself, I'm just going to Control A and Control C. So I'm copying all of the text inside this file here, and back inside my project, I'm going to make a new source file here. Now I'm going to make a folder called vendor, and inside there, a folder called stb_image, just so that I can kind of know that this isn't really my code. I'll make a header file called stb_image.h, and delete everything from this file and just paste in what I've copied. As you can see, it's about 7,500 lines of code here. Okay, cool. Now, if you actually read this file, this is what you should do when you get new files from the internet and new libraries and all that. It basically says pretty simply, do this, right? Define STB image implementation before you include this file in one C or C++ file to create the implementation, okay? So it should look like this. It even gives you an example, right? So what we need to do to actually compile this code once and once only is we basically add a new item. I'm gonna add a CPP file. I'm gonna call this STB image, stb_image.cpp. I'm going to include stb_image.h. But before I do that, as it says over here, I'm going to define STB image implementation. And that's all I need to do. And if I hit Control F7, it's going to compile all of that STB image code. There we go, done. Simple as that. Now the next step is going to be to create a texture class for ourselves so that we can kind of organize all of our code. So I'm going to add a new item. It's going to be a header file. We're going to call it texture.h. I'm also going to add a new item, which is going to be our CPP file, of course, texture.cpp. Going to include texture.h in here. And this is just going to be our texture class. I'll include the renderer in here so that we have access to OpenGL and everything we need. And we can start with creating our texture class. So inside here, I'll make a render ID as we have for pretty much everything. I'm also going to keep track of the actual file path of our texture. I'm going to define an unsigned char, which is going to be our local buffer. So this is just going to be local storage for the texture. And then finally, we also need the width and the height and the bits per pixel of the actual texture. All right, cool. And then inside here, public, I'm going to make a constructor, which is just going to take in a path. That's all we need. I'll make a destructor as well so that we can destroy everything when we need to. A function called bind and unbind, and that's pretty much it. Now, I will make some helpers here, like get width, for example, which will just return the width and height, just in case we want to get that later. But in general, I like to kind of add these things as I actually need them instead of predefining all my class, because otherwise it takes quite a while to just think about, well, I wonder what I want this class to have, when you can just extend it later. Now, bind, I'm going to change a little bit. I'm actually going to put an unsigned in slot equals 0 over here. So what this is an optional parameter. If you don't specify it, it will be 0, which basically allows you to specify the slot that you want to bind the texture to. Now in OpenGL, we have various slots that we can bind textures to. And the reason that exists is because we have the ability to actually bind more than one texture at once. So on Windows, typically with modern GPUs, you have about 32 texture slots. Whereas on mobile, like on an Android or an iPhone, you might have 8, for example. Again, this really depends on the actual GPU that you have and their implementation of OpenGL. You can always ask OpenGL, hey, how many texture slots do I have? But just to give you a rough ballpark, on modern GPUs, you have about 32. On mobile GPUs, you may have 8. That's roughly what it will be, but of course you can just consult your platform to find out. So I'm going to right click on texture and using Visual Assist, just create all of the method implementations. That's just going to create these implementations for my constructor and all of my methods. I'm going to, in my constructor, assign file path to be path. I want to basically initialize most of these things. Local buffer will set to null pointer, width and height to 0. And you should really try and do these in the same order they're defined in. Bits per pixel I'll set to 0. And that looks pretty good. So the only thing I really did was, actually I did do it in order. Render ID was the first thing. 0. All right, cool. So there we go. I'm initializing all of my variables. And then what I'm going to do here is just start loading the texture. So I'm going to use GL call, glgen textures. I'm going to generate one texture and assign it to renderer ID. I'm then going to go ahead and bind it. So we bind it by just calling GL bind texture. Now we specify kind of like what we do with like our vertex buffer, where we actually bind it, we specify kind of what kind of buffer it is or what slot we're binding it to. So in this case, this is going to be a GL texture 2D because it's just a two-dimensional texture. We might talk about the different texture types in the future when we get to them. Render ID is the texture that we're binding. Now let's go ahead and actually load our image. So to do that, we need to include stb image. So I'm just going to type in include stb. Now, of course, this is going to be in vendor/stb image/stb image. If I was actually properly setting up this project, I might have actually included the vendor folder in the include paths for my compiler so that I won't have to kind of do vendor, but this is fine. Now, actually, before we do all of this, let's actually load the image. Now, the first thing I want to do is type in stbi set flip vertically on load. Now, the reason we need to do this, and I'm going to just set this to 1. So what this does is actually flips our texture vertically, so it makes it upside down. The reason we need to do this is because OpenGL actually expects our texture pixels to kind of start at the bottom left, not the top left, right? So the bottom left in OpenGL is 0, 0. Now, typically when we load images, like PNG for example, stores it in scanlines kind of from the top of the image to the bottom of the image. So we need to actually flip it on load. This really does depend on your texture format, so definitely take a look at this. For our use case, for our PNG here, we do need to flip it. So just if you see that your texture is upside down or whatever, you can play with this flag to make sure that you get it the right way up. Okay, the next thing we're going to do is assign mLocalBuffer, which is our local storage for our texture, to be stbi load. Now we're going to have to specify a file name, which is just going to be path.cstring. Then we have pointers to x, y, and channels, which is just going to store all of our actual width and height and all of that. So we've already created variables for this. We just pass in the memory address, and what this stbi load function will do is actually write the width and height and the bits per pixel or whatever into those actual variables for us. So we're passing pointers to these variables so that this function can actually write to them. And desired channels is kind of how many desired channels we have. So we want RGBA, so that's 4. So we're just going to type in 4 like that. Okay, so once we've got this, we've actually got all of our texture data inside this local buffer here. What I need to do now is set up some actual settings, I guess, for our texture that we've just generated here. So the way that we set any texture parameter is we call GL text parameter, and then the type of data we're trying to set. So this is going to be an I for integer. So the first parameter here is the target, which is texture 2D. The next slot is the actual parameter name, which in this case is going to be GL texture min filter. So this is the minification filter. This is how our texture will actually be resampled down if it needs to be rendered smaller than it is kind of per pixel. We're going to have an in-depth episode on all of these kind of texture parameters because like dealing with bitmaps and kind of minification and magnification filtering and like, you know, edge clamping and all of that is a kind of a big topic, then I don't want to just squeeze it in here. So we will talk about this stuff in more detail in the future, don't worry, but for now you can just kind of use these settings and I'll explain them as I go. So this we're going to set to GL linear, which is just going to linearly resample everything. So it will kind of still look okay. It's not going to snap to the nearest pixel, which is what GL nearest would do. We also have to specify the magnification filter, which is if we actually kind of render our texture on an area that is larger in pixels than the actual texture size, so it needs to scale it up. We also need to specify the clamp modes, so GL text parameter I, GL texture 2D, GL texture wrap. Now I call them clamp modes, but they're really wrap modes. So wrap S is the horizontal wrap, so we want it to clamp, which means that we want it to basically not extend the area. The other option is tiling. So we don't want to tile our textures here. So S and T is kind of like X and Y, but for textures. And these 4 parameters you need to specify. If you don't specify these 4 parameters, you're just going to get like a black texture, which is a little bit annoying because you kind of expect them to maybe be on sensible defaults by default, but they're not. So make sure you specify these 4, otherwise you may and probably will get a black texture, but of course that does depend on your OpenGL implementation. Okay, cool. Next step is going to be to actually give OpenGL the data that we've read in here. So we've got a bunch of pixel data inside mLocalBuffer. Let's actually send it now to OpenGL. So the way that we do that is via an OpenGL call called GLTextImage2D. So the target is going to be GLTexture2D. The level, this is at this point you probably want to read the documentation to figure out what all of these are. A lot of these are completely irrelevant to us. I'm going to kind of skip past that. We will look at advanced textures in the future, so we'll cover them then. But for now we want the level to be 0 because this is not a multi-level texture. Internal format is going to be GL-RGBA. That's how OpenGL is going to see our actual format, RGBA. Not the format of the data we're supplying, but how we want OpenGL to deal with our data. Internal format versus format is a huge topic in itself, which we'll probably even dedicate an episode to because people confuse that all the time. But internal format, which is the first format, that's how OpenGL will store your texture data. Whereas format is the format of the data you're providing OpenGL with. So in other words, the format of mlocal buffer. Now, in recent implementations of OpenGL, you should actually call this GL RGB A8. Okay, so you should be specifying the actual bits per channel, which is how you want OpenGL to store your texture. So GLRGBA is kind of deprecated. It will still work on most implementations, but technically the correct modern OpenGL way to do this is actually to specify a number here, which says how many bits you have per channel. All right, so width is going to be mWidth, which is what we read in from our stbi load function. Then we pass in mHeight for the height of our texture. Border, we definitely don't want a border, so 0 pixel border. So format is, that's like the second format, so that's the format of the data we're supplying. GLRGBA is what it is. We don't use numbers here. The type is the type of data, so unsigned byte, right? So we have GLRGBA, and each one of these channels is an unsigned byte. And then finally, we have a pointer to pixels. Now you can make this, you can actually pass in a null pointer here or 0 or something like that if you're not ready at this stage to actually give OpenGL your data. What that means is that you're just allocating space on the GPU because it knows how much space it needs, but you're not actually providing it with data. Now we already have the data, so we're just going to pass in mlocal buffer, just like that. All right, great, and that's really all we need. So what I want to do now is unbind our texture by just calling glbind texture 0. Could also call the unbind texture function. Well, we of course need to specify what we want to unbind, so gltexture2d. Since I've got this code here, I'm just going to copy and paste this into unbind as well because that's really all we need. Cool, so now what we can do is if mlocal buffer, right? So if this buffer does actually contain data, we're gonna use stbi image free to actually free this local buffer. Now in more complicated setups, you may want to retain a copy of the pixel data on your CPU because you might want to sample it or do something, whatever you may want to do with that data. So that's totally perfectly okay as well. Totally perfectly okay. That's also kind of acceptable, right? So you may want to have something in the constructor that's like, you know, keep local data around or something like that. We don't really care about that, so I'm just freeing it, but that's why I kind of made this a member variable, mlocal buffer, in case you kind of want to store it. And that's it. Now finally, over here inside our destructor, we could delete the data. Now we've already freed the data in the constructor, so we don't have to deal with that here. But we do need to actually gl delete textures to delete our actual texture from the GPU when this object gets destroyed. So we'll just gl delete textures and pass in that renderer ID. Now bind is an interesting function because we already know how to bind textures. It's really just this, right? But what we can do here is actually specify a texture slot, and we do that by typing in gl call gl active texture. Now active texture takes in an integer, which is just really a gl enum, which is going to be which texture slot we're currently activating. So again, this is kind of like the whole state machine selecting thing in OpenGL. We basically say, hey, I'm gonna make gl active texture slot 16. That means that the next texture that I bind will be bound to slot 16 until I call gl active texture again with a different slot. So in this case, the way that we specify slots is we use enums, right? So gl texture 0 like that is the very first slot. Now we have texture 1, texture 2, whatever. If you actually look at what these are equal to, they are of course just integers, and they go all the way up to 31, right? So you have 32 texture slots. Now this does not mean that your platform supports that many textures. It's just 32 happens to be the maximum that the OpenGL specification allows. Your platform, as I said, mobile may have like 8. So you should query and find out how many you have if you are going to use this many texture slots, which you probably usually won't be unless you're making a really big game, because there are ways to kind of, you know, reuse textures, and we'll talk about that later. But anyway, we have all these texture slots. Now in this case, we are specifying an unsigned int. Now this will be something like 0 through to 31. So what you can do is just type in gl texture 0 plus slot, and then it will add the slot, because if you look at these definitions, you can see that they are actually consecutive numbers, right? They do just count up. So that's our entire texture class. That is all that we need to actually give OpenGL our texture and for us to render it and all of that. All right, so I knew this was going to be a long episode, but let's keep going and let's actually see something on the screen, because that is the goal for today's video. So back inside application, let's set all of this up. So I'm going to, at any point really, just type in texture. I'm going to give it the path, which is res/textures/Cherno logo.png. I'm going to include texture up the top because I haven't done that yet. And scrolling back down, I'm going to bind my texture. I'm not going to pass in a parameter, which means it's going to be equal to 0 by default. One thing I need to do, by the way, with my shaders before I forget, is we need to, first of all, fix out this awful error I made last time in which I passed in, and well, basically I make this map have an unsigned int, and I use unsigned int a bit too much, it seems, because this get uniform location function, I even check to see if the location is -1 here, because that's totally valid. That just means that it couldn't find our uniform. But I'm assigning it to an unsigned int here, which is obviously never going to be -1. So all of this should be an int, not an unsigned int. When you're dealing with uniform locations in OpenGL, the type is a 32-bit integer, okay? So int, and this should also be int. And if we go back to our header file, this should be int, because that's our uniform cache. And also this should be int. And I think that's all the ints. If I compile this, hopefully it'll work. And yep, we're all good. Okay, that's one thing I need to clear up. Now, one thing that we need to do is we need to actually tell our shader which texture slot to sample from. And the way that we do that is via a uniform. Now, this isn't really an integer slot. It's something called a sampler slot. And this is a bit hazy and a bit weird. Basically, what we need to do is send an integer uniform to our shader, and that integer is the slot that we've bound a texture to that we want to sample from. And then in the shader code, we can actually use that sampler or that integer that we've passed in to actually sample that texture and do what we want with it, okay? So that's how that works. So to do that, we need to write another shader uniform function here, which is going to be called setUniform1i, which is for integer. And then we take in int value like that. I'll copy and paste this 1f function and replace this with int, and that's pretty much it, right? Just make sure you replace uniform1f here with 1i. Okay, cool. Back to application. So now that we have this, we can actually set that up as well. So shader.setUniform1i, we're going to call this uniform u_texture, and we're going to set it to 0, okay? Because we've bound our texture to slot 0. So that 0 needs to match whatever you're passing in here. If I had passed in like texture bind 2 or something to slot 2, we would be passing in 2 here. Okay, let's undo that. All right, cool. So there we go. Pretty simple stuff. Now, one thing we haven't done is actually created something called texture coordinates. So what we need to do is actually use something called a texture coordinate system to tell our geometry that we're rendering which part of the texture to sample from. So our pixel shader goes through and renders and rasterizes our rectangle, right? It just goes through the rectangle and draws every pixel. The pixel shader or the fragment shader is responsible for determining the color of each pixel. So what we actually need to do is somehow, when it's up to rendering a certain pixel, tell it to sample a certain area of our texture to retrieve what color the pixel should be. Right? If you think about it, it's actually kind of simple. It's not too complicated to understand. Hopefully this makes sense. If you don't, drop a comment below and I might make a detailed kind of in-depth video on how the rasterization works and how texture sampling works and all of that stuff. But basically what I'm saying is we need to say that, hey, the bottom left of our rectangle on our screen is like coordinate 0, 0, and the top like right is the other end of the texture, which in OpenGL terms is going to be 1, 1, okay? Because textures we don't really tie textures to certain sizes, or we don't tie texture coordinates to a certain resolution, because the texture could be 64 by 64, it could be 1024 by 1024, it could be like 57 by 19, it could be anything, right? So what we need to do is basically specify for each vertex that we have of our rectangle what area of the texture it should be. And then the fragment shader will interpolate between that, so that if we're rendering a pixel that's like halfway between two vertices, it will pick the texture coordinate that's like, you know, halfway between the two vertices. So let's set that up. So to do that, if we come over here into our positions, we know this one is the bottom left. So that's going to be 0 by 0. I'm adding another vec2 basically. I'm adding 2 more floats to each vertex here, which are our texture coordinates. Now this is going to be 1.0, 0.0, because it's the right side, right? So 0.5f is the rightmost edge of our actual rectangle. And so I'm setting that to be 1, which means sample from the right side of the texture. This is going to be 1.0 and 1.0 as well. 0.5, 0.5 is the top right, and that's what we're also matching with our texture coordinate. And then finally we have 0 and 1.0. Now we need to add this to our vertex buffer layout. Again, with our API, it's really easy. We just do this, layout.push 2 more floats, right? That's it, that's all we need to do. We also need to actually expand this vertex buffer to contain these extra things, right? So now instead of having 2 floats per vertex, we actually have 4 floats per vertex. So we'll increase this to 4. And finally, we need to go into our shader and basically rewrite the whole thing. So in our vertex shader, we now take in a texture coordinate at location 1, which is a vec2. I'll call it, I don't know, text coord or something like that. And now we're faced with something a little bit new. We need to get this texture coordinate into our actual fragment shader, because check this out. The way that we're going to actually sample our texture is, as I said earlier, by using that sampler2D uniform, right? So sampler2D u underscore texture, which is the uniform that we set over here, we set it to be 0, right? So we need to sample this somehow, and that's this uTexture uniform. And the way that we do that is we actually work out the color. This returns a vec4, which is kind of like our text color. I'll just write this out for you guys. Text color is going to be texture, the texture that we're sampling, which is uTexture, and then we need to specify those texture coordinates, right? So how do we actually specify our texture coordinates? Because they're in the vertex shader. So the way that we kind of send data between the vertex and the fragment shader is by something called a varying. Now, in modern OpenGL, this is kind of the in and out system that we're already used to. Similarly to how we can actually input data into the vertex shader by typing in and also output data from the fragment shader by typing in out, we can also output data from the vertex shader into the fragment shader. And the way that we do that is we type in out. Now this is going to be a vec2, of course, it's our texture coordinate, and I'll call this v underscore text coord. V stands for varying, which is what this is called. And then I'll assign v text coord to be the text coord that we take in from our vertex buffer. And then similarly in the fragment shader, I'm going to type in vec2 v underscore text coord, just like that. And I'm going to use that text coord over here so that we actually sample that specific texture coordinate. Because remember, this fragment shader runs for every pixel. So we need to know the precise location in the texture to actually look up so that we can draw that pixel from the texture in our actual scene. And that's what this whole sampling thing is about. Again, I'm sure we'll discuss this in the future in more depth. Okay, cool. So now instead of assigning this to U color, I'm going to assign this to text color, which is our actual texture lookup color. And everything looks pretty good to me. Now, I did write a lot of code and I'm not sure if this will work because I haven't even run this program once, but let's just hit F5 and who knows, maybe this will just be beautiful. Okay, so we get a nice little OpenGL error here. If we look at the actual console, we can see it's 1280. This is because this is not GL clamp, it's supposed to be GL clamp to edge in more modern versions, so we'll just set this to be GL clamp to edge. Now, one other thing that I noticed when I was debugging this as well is the local buffer was actually null, which means we're not loading this in correctly. So let me just refresh this and figure out what's going on with our actual texture. So if I just refresh this, it doesn't look like we've actually got the textures in here for some reason. And that's of course because this resources folder wasn't inside my project directory. Make sure you put it into your project directory. And now if I hit this refresh button, you'll see we have textures in here and all of that. So this should work better now. Let's hit F5, take 2. All right, beautiful. So we see the Cherno logo. Now it looks like absolute trash. Why does my logo look like trash? Well, I don't know if I should end this on a cliffhanger or if I should actually finish this. I know why it's not working, obviously, but this could be fun. You know what? I usually would leave this on a cliffhanger, but this is just such a beautifully long episode that I think we might as well finish it. It's because I don't have blending enabled. And of course, as you saw, that Cherno logo did have areas of transparency. So there's no transparency being rendered right now. It's not blending at all. That's why it's coming out weird. To fix that, we just need to set up our blending function and enable blending. There will be an episode on blending and transparency in the future, 100% guarantee that. Let's just make this work now for the time being. So if I close this and I go back into my application, or in fact into my render, I think, did I do kind of OpenGL setup stuff in the renderer? I don't think I did. No, I didn't. Okay, so we'll do this in the application file for now. What I'm going to do is scroll up here. Once I have my OpenGL context, it's kind of part of the OpenGL initialization, I guess. I'm going to set up GL blend func. So I'm going to set a blending function, and this is going to be GL source alpha. Not source 0 alpha, GL source alpha, and GL1 minus source alpha. So what we're doing here is we're basically defining how OpenGL is going to blend alpha pixels, right? So this really does require its own episode. But essentially we're saying that for the source, take the source alpha, and when you're trying to render something on top of that, take 1 minus that source alpha, which will basically get the difference of that. So it's just really it really is just a mathematical equation. Like literally 1 minus the source alpha is what the destination alpha is going to end up being. Again, episode on that in the future. And then finally, we do need to also enable blending by calling GL enable and then GL blend. Okay, and you can do this in any order, doesn't really matter. I kind of like doing it in this order just because we enable blending and then we kind of set up the blend function. Let's hit F5 and we should see a beautiful Cherno logo. And you can see, there we go. Now, of course, it does look a bit stretched because the rectangle that we're rendering is not square because our window is not square, and this is kind of based on window positions. But if you can kind of get over that, you can see that we have a beautiful Cherno logo rendering, and that is how we use textures in OpenGL. If you have any questions about textures that you want answered, leave a comment below because I am going to make a lot of related videos to textures in the future. Textures are a really big deal of graphics programming and all of that, obviously, so we are going to talk a lot more about them in the future. Other than that, I hope you guys enjoyed this video. If you did, you can hit that like button and let me know what your thoughts are about all this stuff in the comment section below. As always, huge thank you to all of the Patreon supporters that let me make videos like this for all of you. If you want to support this series and see more episodes and get videos early, patreon.com/thecherno, and I will see you guys next time. Goodbye.